Non, j'ai pas forcément. Sinon, je ferai sur l'écran peut-être. Voilà, on voit trop la table. Attends. Non, il faut que tu avances la caméra peut-être. Ah, mais c'est bon.
Ouais, c'est bon. YouTube, il y a un décalage de 30 secondes sur YouTube. C'est logique.
Comme ça tout le temps?
Non, non.
Ah oui, mais c'est
non, mais ça suit. Hein.
C'est pour... Ça va être compliqué.
Bon, là, c'est bien, là, tu peux parler en face.
Il va falloir se gérer.
On va attendre 5 minutes et on va démarrer. Okay. Okay. Good afternoon to all of you. So it's a very pleasure to welcome you. Afternoon or maybe morning for some of you, because I think some are in Canada or in Brazil and it's the morning. So this is the last conference concerning the Fun Glass Days. We have 5 events. This is the last one. And well, we have 4 speakers today, which are scheduled. Yes, 4. But unfortunately, one of them could not attend to the conference because to the COVID issue. So sorry about that. So the person from Corning is there, but person from EXBlue is unfortunately cannot provide and deliver the talk today. So today we have, you can follow us also on YouTube channel, and we'll start with Sylvain Danto from l'Institut de la matière condensée de la chimie de Bordeaux. And Sylvain will talk about
multimaterial fibers and ribbon fibers.
Ribbon fibers and multimaterial fibers. For people which are interested in glass, you know that glass it's very useful nowadays in many technology, and fibers is one of the technology which is, let's say, maybe where we are the most development in glass material for the future, maybe for the infrared, for sensing, for bio application, for lasers also. So there is a lot of place to work with glasses and in fibers, mainly in fibers. So Sylvain is talking about those multimaterial fibers, and I think you have something like 30 minutes.
No, less.
Less than that? Okay.
You told me 20 max.
20 max plus questions. So, okay, it's up to you.
Okay. Hello, everyone. Do you see me?
I think so.
Okay. So, bon dias. Bon dias. Guten Tag. Hello et bonjour. Voilà. So this is a very...
I think you have to share your screen now.
Share the screen.
You must, I don't know, afficher la barre de tâches. Non. C'est là. So, where is your presentation? This one? Okay, let's start. Now, I think here you can do it like this. I hope it's okay. Let's wait. See? Yes, but this one, you don't have the screen over there. Ah, yeah, I see. Because you're not on the good screen.
This is this one that you have to put full screen.
Okay, so let's try again. Alors, sorry about that, just a starting point. It's always difficult. Partager. So which one is it?
Voilà, la présentation est là.
This one?
Ça, c'est des slides. Partage ça.
This?
Oui.
Okay. You know how to do it on your computer?
Ça. Ah, tu as besoin de ce mode-là?
Il est là, il est là.
C'est surtout public, quoi. Toi, tu veux voir ça? Peu importe, moi je me
là,
mais c'est pour les gens qui seront là, quoi. Arrêtez, c'est dépend.
C'est pas là, le pardon?
C'est où le mode présentation? Ça, je connais pas.
Okay. So
it means this is shared.
I think now you can see the screen of Silva. Yes, I think it's shared. Okay, and you can move. Okay, let's go on.
Okay, so welcome everyone. Thanks for being connected. I think it's probably very early for you in America. So I will give you a brief overview of the research we are conducting in Bordeaux on the fibers. So with a strong focus on the multi-material fibers, so as you will see, this is a brief overview, but at the end I will include my email, so please don't hesitate to contact me if you have any questions, especially knowing that the purpose of this presentation is to collaborate and to initiate discussions. So the overall motivation of the research.
C'est toi qui ouvre ton écran, ça.
Please give signs, raise a pouce, a stamp if you are live.
Maintenant, tu peux mettre une présentation.
Attends. Okay, so let's start again. Yes, I will have to come back here. Voilà, c'est ça. So we have 30 minutes would be good. Sorry for the starting. So the overall motivation of my research is to implement a drawing capability in Bordeaux, and then with a focus on specialty optical fibers. So which means having into fibers new materials suitable for thermal drawing, and new set of materials. So not only one material, but having a combination of different materials, new fiber architectures, meaning, for instance, as you will see, going away from pure cylindrical fibers, but presenting, for instance, rebound fibers, and then having, of course, these fibers used for improve or new functionalities. So, so just the roadmap of the research. The first step is, of course, the material selections. So I will detail everything, but once the material is selected, so we have the preform design, which is an important step after fiber drawing, and then the post-processing, because having the fiber made is sometimes not the end of the story. We can still keep functionalizing the fiber to develop specific properties. So considering the materials, of course, the starting point for us is the glasses, because in the group, the history of the group is have been made on developing new type of glasses, for instance, phosphate glasses. But these glasses, What is this? These glasses can be, of course, doped with luminescent ions or noble metals or nanoparticles. They can be combined with polymers, or all polymers can be drawn together, alone, or the glasses and all polymers can be drawn with metals and or alloy to give electro-optic fibers, for instance. So this, once we have selected the materials, the preform is designed. So the first standard work that we make once we select a material is, of course, to verify that this material is suitable for drawing. So we do simple solid core preforms, which are drawn into fibers. But then, of course, an important work that we do here is developing core-clad, let's say, regular preforms and fibers for regular optical property applications. Another thing that we developed recently and that we worked a lot on now is stack and draw revisited. So this is the stack and draw that was historically developed for photonic crystal fibers that we have modified to develop specific ribbon fibers with complex shape. Multimaterials, which means a combination of glass, polymers, metals, the ribbons, as I discussed already, and then research that has been started. And then maybe, I don't know if we'll talk about it today, but the 3D printing, which is another very important research that we have here, and then can be looked with the drawing. So for instance, we can develop filaments that are used for the 3D printers, for instance. So then the fiber drawing step on the post-processing. The post-processing means, for instance, direct laser writing, as we see on as an example on these pictures. On the pictures on the top right, this is a flat fiber, silver photosensitive fiber, silver phosphate glass that has been functionalized using focused femtosecond laser. On top of that, because we generate surface, we can functionalize the surface with, for instance, molecular grafting. We can use as well some combination of laser inscriptions and etching to design, to get some topology, the surface of the preform or of the fiber, depending. The polling, which is something that Mark will discuss after. On some, I mentioned the phase change. This is something I worked in the past. We are not developing that yet, but this is something that exists into fibers, which means having some phase change between glass and crystals into the fiber. So choose to be a bit more specific. If we give some examples of materials that are developed here. So first of all are the phosphate glasses. There are, let's say, two major types of glasses, or phosphate glasses. So the silver doped glasses, photosensitive materials that are developed for photosensitive applications in combination with femtosecond laser inscriptions. And then otherwise, something important is the phosphate-based glass doped with rare earths for laser applications. So I recall here a few the main properties of the interest of the phosphate glasses. Here, just these pictures. This is the laser mirror coming from beneath the laser megajoule that to generate high power lasers. Here, example of homemade preforms on fibers, photosensitive preforms. And here is an example of a phosphate preform doped with neodymium. Here, example of a study that we conducted in the past to develop phosphate fiber lasers. So this is the study was conducted using neodymium, but we have conducted other study with other rare earths like erbium or ytterbium. Show you examples of doping into the glass matrix. Considering the shaping, so of course, an important thing are the losses into the fibers. So we work on developing for all type of glasses on the systems, some core-clad preforms. Here are examples. There are different methods for doing that. For instance, here we did it by employing a method that is called building casting. So we do first the claddings, and we reverse the preforms, and once the preforms, the inner part of the preform is emptied, we cast the glass inside. And then, of course, after everything is annealed and drawn into fibers. So we see example of fibers here and losses. So the average losses so far for the preforms on fiber, for the fiber we made are between 1 and 2 dB per meters. But we have a strong work in the group, of course, to lower those losses. Another example of research that is conducted in the group concern the germano-gallate glasses. So those materials have been historically developed by the US Army. Materials are transparent into the mid-infrared up to 6 microns, and then they have superior mechanical properties. So it was really and still is the key interest for those materials. And then after the challenge was to draw these materials into fibers. So here is the matrix that is the starting point, so gallium, germanium, barium, oxide. And then after looking for several combinations of doping elements, so we found that modifying the matrix with rare earths like lanthanum or yttrium help drawing the materials into fibers without loss, of course, without losing the interest into the infrared, the extension of the window in infrared, and without losing or without reducing the mechanical properties of the fibers. So here is an example of a study that were conducted with the team of the COPL in Canada. Really a collaboration with the team, and which is still going on these systems. So we see that the fiber were developed, and then the losses are at this point quite high. So as you can see, between 6 and let's say 3.5, 4 dB per meters. It was the beginning of the study. Now we are working on with using glove box, for instance, working on the purity of the precursors, on other methods, working strongly on lowering those losses. Now, if we move to rebound fibers, an interest, the interest came at first a while ago when developing these silver phosphate photosensitive glasses. Those glasses are sensitive to interesting for laser inscriptions. So we weren't able to make the fibers, but then came out the issue of the curvatures of the fiber. So of course there are solutions to solve this issue, but an idea came out is why not developing flat surfaces straight from the beginning. So the question is then, can we prepare a flat preform as thin as possible, and are we able just by pulling on it to maintain the geometry of the preforms into the fibers? So the answer was yes. Actually, the method works quite well. So we see that if we have defects into the preforms, if it's not, for instance, perfectly optically polished, the defects into the preforms are still visible into the fiber. So we worked on this process and improve it. Here examples of glasses. So we have on these pictures where oxyfluoride glasses developed a few years ago in the group. So depending when the TG of the glass increase, we are able to get thinner and thinner fibers. For instance, we were able to draw glass slides with a ratio between the width and the thickness of 20, and then this ratio of 20 were maintained from the glass slide to the fiber. So we see that with such ratio, we still talk about fibers, but it's not exactly optical fibers anymore. We use them more for generating, we use the method for generating surface, and after we can use this surface for functionalization. So here's an example I mentioned already, considering the direct inscription of patterns indirectly into the systems using femtosecond lasers. Another example developed currently in a group is working with borophosphate glasses. Those materials are interesting because they are very high nonlinear optical properties. So again, the interest came really from the combining both the shaping of the materials and the pooling into the systems. So I show you brief results of this. Maybe Mark will discuss more on the pooling again after. So here is the quick scheme of the system. So we apply the voltage into the materials while we heat it at the same time, so generating some diffusion of sodium. We break the symmetry of the materials. So this is really roughly the methods, but I would say that before applying the pooling on these materials, the first challenge was to make the fibers. And we see that actually this is something that is now developed well and works well in the group. This is George who is doing that with us as a PhD. So here is an example of borophosphate preformed, which is optically polished and then transferred into the fibers. As we see, we have a ratio of something like 1:10, which is enough for many applications. And we have some widths that can go up to 2 or even 3 millimeters, which is at the same quite large enough for many applications. So here are examples of transfer of the pooling on these systems. Here at the top is the electrodes that have been prepared at the ISM. And then this electrode is applied on the fiber, and then the pattern is transferred into the glass. Another example of research that we conduct currently using these fibers is that we call the stack and draw revisited. So as you know, there is this method that are historically developed many years ago to prepare photonic crystal fibers. So some fibers are drawn first, and then they are stacked together to make a new preform, which is drawn again. Here we applied the same method, but instead of working with cylindrical fibers, we prepared a lot of ribbons, or ribbons. Yes, and then of course we have to assemble the preforms, which means combinations of temperatures and pressure, and then we heat under pressure the preforms, and then this preform, when it's stacked together, is drawn again. Here, just to show the power of the demonstration, this is a work that were made by a previous postdoc, Clément, a few time ago. Now, so just to show really the interest and the power of the method, he had this idea to make a preform with more than 30 pieces of glasses stacked together to represent the logo CNRS. So we have the C, we have the N, we have the R, we have the S here. So it was transferred from the preform to the fiber. So as we said, we had the joke. Next time, the next challenge is to do the same, but with University of Bordeaux, which will be much more complex. But at the same time, a bit useless. But anyway, and then once, this is really the point, is to show that actually the method works. And it's working with many glasses. And for this example, on the next one, actually what we use were sodalarium glasses. But we have transferred the method with borophosphate glasses on other type of systems. So another pieces of information that I think is interesting for you is that, considering the stack and draw methods, what can be inserted into the system is, of course, holes, but holes that generate cavities that can be filled with gases or liquids or anything else. But at the same time, we can fill holes with metals. So here we have some examples of aluminum wires that were inserted into the preforms, so square electrodes, cross or flat strip electrodes. And then this stacking were homothetically drawn into fibers. And that we see that you can maintain the shape of this, both the fibers, overall shape of the fiber, but at the same time, the shape of the electrodes. So this is I would say, a refinement of the method that can be eventually used if we want to not only have some electro-optic effect into the fibers, but on top of that, if we want to generate some specific tip effects at really a specific point, a localized point somewhere into the fiber. Here is an example of a brief simulation that were performed at the time. And now to give some example of applications of this method. So here is a stack and draw preforms. So this preform is made of, it's a hollow core preforms made of soda-lime glass for the cladding, a soda-lime core doped with neodymium to increase the refractive index to have some guiding effects between the core and the clad. And inside were inserted 2 electrodes. And then this preform is drawn into fibers. Here in transmission, we see the core. In reflection, we see the 2 electrodes. And then by connecting a potential to the electrodes and raising the potential, that what we observe is that we can generate a discharge at the tip of the systems, and then we generate a plasma discharge at the exit. So this plasma can actually be analyzed using the core of the fiber. So we apply the voltage at the exit, and then using the inner fiber, we analyzed it. So for the demonstration, here, this is an example of a demonstration performed into the air, where we see the peaks coming from the discharge of the hair at the time. The same method were applied using a slightly different assembling. So this case, in this time, what we have is a polymer cladding. This polymer is drilled and filled with 2 metals, 2 metallic wires that are drawn into a fiber, a relatively large fiber. And within this fiber is inserted another one, an optical fiber. In this case, this is a commercial fiber. But the same, of course, the same thing could be made with some homemade fibers, some of the many fibers that we developed in our respective groups. At the end, what we get is something that looks like this. We have the assembling of the polymer, the electrodes, and then the commercial fibers in this case. Now we see better here downstairs. And then here, once again, the potential is applied to the electrodes. The plasma is generated, and then we can use the commercial fibers inside to analyze the plasma remotely. And then a demonstration was made using 3 different atmospheres: nitrogen, argon, or oxygen. We have some people working currently on this research axis to improve the process, to have a stabilized plasma, to lower the damaging of the tin electrodes at the exit, because this is something that can actually occur. And now the issue is solved, but at the time we had quite a strong damaging of the tin electrodes. Now it's not the case anymore. And again, as I said already, a research that is now conducted is to replacing these commercial fibers by homemade fibers that are, let's say, for instance, more transparent into the infrared if we want to observe other effects. I think it's it. So as a conclusion, what I show you briefly today is the summary of the new research activity that we have here. Just considering facility, we have 2 draw towers. I think many of you know it already, but we have 2 towers, one going up to 1,000, another one going up to 1,400 degrees Celsius, if you have some need for drawing glasses. So we demonstrated that we can having new materials into these fibers, a lot of type of glasses with many applications, especially many glasses transparent into the infrared up to some 5-6 microns, which is very useful for sensing, for instance. And then we are targeting many applications. And then just to finish, the new challenge is, of course, having more materials, new shapes, and then improving the overall processing of the method, including, of course, lowering the losses. I think this is it. thank you very much. Thank you to the co-workers, and thank you, everyone.
Thank you. So we have time for questions from the audience, or maybe from the Zoom session. So just raise your hand or feel free to ask questions. What? No, it's okay. There are 28 persons each other. And yes.
I have a question for you. You have shown at the end that you are using commercial fiber plus polymer.
Yes. Yes.
Do you draw it after?
No, no. We draw only the cladding. We draw the cladding first, and then after, once the cladding is drawn, we insert the commercial fiber inside. But this is part of the challenge, actually, is that we have to, it's not such a complicated challenge, but we have to be at the good target, yes. So we have to, one thing, for instance, we observed is that the diameter of the electrode is important, because if the electrodes are too small, they are hard to connect, and then the resistance is really strong. So we have to have quite relatively large preforms with large metallic electrode. And then the hole that has to be at a good ratio, so that after we target, we know that we want to be at 130 microns inside. So just knowing this information, we apply the drawing parameters.
Another question? No? No questions. From internet, from the Zoom session, I have no questions. Okay, so if so,
thank you again.
Let's thank the speaker again. Now we can switch to the next speaker. Marc Dussault.
Je sais pas s'il faut que j'arrête ça.
No, I don't think so. Don't touch.
Don't touch.
I really don't know how it's working. So just. Yes, it's this.
Okay, dear Chairman.
Yes, Mark, you can start.
I can start. Thank you, Lionel. Thank you. Il a cassé la chaîne.
Okay.
Sorry for this small technical problem. All right, so let's start. Today, I would like to discuss with you about multifunctionality in glasses by imprinting thermoelectrical process. So we'll discuss about glass chemistry, as you can see with these first pictures taken by my friend and colleague Fred at the lab. And the other very nice pictures represent the thermoelectrical process. So as you can see, we will discuss of some plasma, high electric field and stuff like that. The first example I want to show you, it's a chalcogenide glass that has been discovered to be a very good glass for thermal pulling and to give some very nice functionality and very multiple functionality in this kind of glass. So that will be a first very nice example. The second examples will be some nonlinear optical properties in iobate amorphous thin films. And then we will finally discuss about plasma-assisted pulling to tune the surface property of glasses and notably to be able to interact with molecular systems like liquid crystals. So let's start with glass chemistry. So we all know glass is a very good material, especially for its optical properties. That glass has permitted to break lots of barrier and frontier and to develop a lot the communications in the world. That's very nice, but if we are a glass chemist, we know that we can do also many more for many more applications, because we can change a lot the glass compositions and then be able to develop some new synthesis, new glass depending on the wavelength domain, the transparency domain where you want to work. So that's the first thing, very interesting, as you are a glass chemist, that you can work with oxide glasses to work in the visible, or you can work with, let's say, why not chalcogenide glasses if you want to work in the infrared or mid-infrared domain. So the choice of the glassy materials permits to choose the transparency domain. But if we continue a little bit more and we want to create such kind of device, like a planar device, which is, it looks like a microelectronic device. So you need several optical functionalities. You need to be able to guide the light, to have diffraction, emissions, and also nonlinear optics. On all these kinds of functionalities, the glass cannot do it alone. So you need to work on it, either on the shaping, the composition, but also to add some, to develop some new process to induce this new functionality. I have here another example, which is also a 2D photonic device, but this one is a infrared spectrometer on the ship. So it's a very, very tiny infrared spectrometer. You have the source, you have the different interferometers that are based on the nonlinear optical response. You have also the detections, of course, and for one of the arms, you see, you have some microfluidic channels. So which means that for these arms, where if you want to detect something, you make a real, let's say, a real spectrometers that can detect different species. You may want to add to such kind of optical circuit also some chemical functionalities. And for example, to attract the some biological system on the surface to be able to detect it. So you see that starting for just one properties, which is transparency, you may want to add to your glass different kind of functionality, nonlinear optical response, or a different kind of optical properties, but also why not chemical or biological properties. This is what we try to do here in Bordeaux with all my colleagues. So for this, we have a good team of glass chemists, but that's not enough. We need to prepare the glass and then to induce some new functionality in this glass. So one of the process to be able that we can use is laser irradiations, for example. And the second process that I will discuss today is thermoelectrical polling. So if you want these processes to be adapted to the materials, then you need not only to work on the transparency in the materials, but also on its photosensitivity. For example, if you want to develop a glass which is adapted to laser irradiation. And if you want to develop a glass for thermoelectrical polling, then you need to be able to control the ionic or electronic conductions of your glass to be able to be adapted to the process. So that's very, very important in our strategy, research strategy, to always adapt the materials to the processes in order to obtain the good functionality that you want to obtain at the end. And this is then our approach, multifunctional approach, but also at different scales. All right, let's continue, and let's now try to introduce this thermoelectrical process. So this is a very easy process. In fact, you just need to put your glass between two electrodes, heat a little bit the system, and then apply a high electric field to the system. The idea is to work in a charge dissociation regime, which means that you need to dissociate charges. And one good example of this charge dissociation is the typical depletion layer in mobile cations that we observe at the anode surface. So you can see here at 0, I hope you can see my mouse. This is the anode surface. Then you go inside the glass. This glass at the beginning had 12 atomic percents of sodium. And during the process, you have removed all the sodium in these small layers. That's very interesting because this first process, this first effect of the process will induce huge changes in compositions. And that's the first lever to be able to control the physico-chemical properties of your glass. So if you change the composition of the glass, typically you will change its properties. Very easy. That's the first lever. Change the compositions in order to get new properties. And the second one, it's the induced phase charge that you can obtain inside this layer. So you can have a static field inside the glass that can be extremely high, as you can see, up to the gigavolt per meter. And this allows different kind of electrical functionality, but also second order optical response. So please try to remember these two levers that we can use to induce new functionality in this glass, in different kind of glass. So changing compositions first, and then this static field that we put inside the glass matrix also, which is the second lever to get new functionality. The second point, which is very interesting, is that this kind of process can be developed as an imprinting process. So if you don't use a classical homogeneous electrode, but if you use an electrode which is patterned, then you can transfer the pattern to the glass surface. The very nice example here is the work from Lipovsky, who has transferred the coin inside the glass surface. Very easy. In this case, the second thing which is very important is that you will have the opportunity to play with the field geometry. So you will be able to choose the electrode in order to select the different geometry of your electric field applied to the glass surface. So this is two examples, one where the electrode is just a change of topology, and this one where the electrode is juxtaposition of different conductive and non-conductive area. All right, so now let's go to some examples to show you what we can do with this very simple process. So I want to focus on chalcogenide glasses. For people who don't know, chalcogenide glasses are these glasses here, which are developed for the infrared domain. And in these glasses, there is no oxygen. So the anions in these glasses is either sulfur, selenium, or tellurium, for example. They are very well-known glasses for infrared vision and also to create photonic circuits for the infrared domain. So we to prepare such kind of glass, of course, if you don't want oxygen, you don't want water, you don't want anything, you need to prepare everything under controlled atmosphere. So everything is prepared in glove box, then it is sealed inside silicon pools and then melt to get the glass, as you can see here. Okay, so we take this kind of glasses and we have study this ternary diagram where you have germanium, sulfur, and sodium. So we play with different compositions, changing either the sulfur content or the sodium content. Okay, the first thing we do, because we are glass chemists, we want to know the glass structure. So it's very important for us to know very well the materials that we are making. So for that, we do Raman spectroscopy, for example, where you have here the different kind of structural units which form the glass structure. So you have the tetrahedral germanate units, where am I? Here, and the antimony units here, which are either connected by just a sulfur bridge or by sulfur ring, sulfur chains as a function of the sulfur content, of course. If you change now the sodium content, you will see that the structural changes are less pronounced. Sorry, you still affect a little bit the germanate networks and quite a lot the antimony environment. But as you can see in this top figure, the Raman spectra are not so much modified. So we can say that the sodium in such kind of glass is maybe interstitial. So it's inserted in the glass, but does not modify the structural units in itself. Not so much, at least. All right, so let's continue. We take this glass, we make the polling, and we obtain such very nice depletion layer, as you can see. So the guy who has measured this is here, it's Antoine. It's 6 microns thick layer of sodium depletion, you see. So you modify the glass for a layer of few microns, depending on the composition, of course. This is just an example. And then we try to look at the glass structure. So we use this imprinting method and we do some Raman measurements. And we compare here the very tiny changes in structure that we observe by doing this Raman difference spectra here to the first ones that I have shown you just before. Just before, these spectral changes were obtained by making the glass by going to the melt. So you start from the melt, you quench it, and you obtain this different structure. Here, the change of structure is obtained at 170, 200 degrees. So it's far away from the melting temperature. And all this is obtained just by moving the ions inside the glass. So that proves, this similarity proves that this glass is very flexible. You can change the structure, move the sodium, insert it or not, and the glass structure will rearrange very easily. And the very nice thing is that you can do it at micrometer scale, which means that now, as you can see, the changes of structure that we can map in Raman are very well controlled at the micrometer scale thanks to this imprinting method. So that's, for me, the most important things that you need to remember, that you need a glass that is flexible and where the polling can really arrange the structure without destroying everything. So now let's go further. What can we do with this depletion layer and with this change of compositions? The first thing we can do is quite easy. We can look at the refractive index change. And if you look at the index from the anode side to the cathode side, you have a huge difference of 5, 10 minus 2. So that's the first very nice properties that you can tune, is the refractive index. The second one that you can tune is the glass chemical reactivity. So we put this glass in a solvent of ethyl diamine in DMSO, and you can see here the dissolution rate of the glass, okay? So that's a pristine glass, it's linear. The more you put the glass inside the solvent, the more you remove mass, and that's linear. But if you have a poured glass with this first layer, you see that you have a first very, let's say, much more rapid dissolution, and then something which is parallel. So in this zone here or here, this graph depends on the glass compositions. In fact, you can see the change of dissolution rate. So you have a very different chemical reactivity after and before polling induced by the change of composition. All right, so what can we do then with this? Then the first, if you look to the refractive index, then we can pattern the refractive index and make some microstructured optics like this series of micro lenses that we can obtain. And if you go to the chemical selectivity, selective etching, sorry, then we can get some very accurate pattern of the topology with some depth, which are quite important here in the order of almost 3 microns of depth, which has been obtained here. So you can obtain some quite precise patterns like this spiral, for example. So you see here, it's exactly the same process. We are using exactly the same change of structure, change of compositions, and we can tune the optical functionality or the topology of the glass very accurately thanks to this imprinting process. All right, so now we will, this is a list of other functions that we have obtained in this very nice glass. So optical properties I've shown you. In chemical properties, you have the selective etching. I have not shown you yet the nonlinear optical response on surface electrical potential because I have no time. And I would like to add also the fact that we have developed a chemical functionalization of the glass also. So we love this glass and we have lots of examples and you can see all the reference if you are interested. I will now switch to the second topic, very interesting one. It's about nonlinear response. So if you remember, there were 2 ways to change the functions of my glass. The first, I changed my compositions. That's the example I have just shown you before. And the second one is the internal field. And the internal field gives second order optical properties. So what about nonlinear response, nonlinear optical properties? So to study, the very simple way to do it is to write the polarization equations like this, where you have the linear response with the chi1, which is linked to the refractive index, for example. And if the laser power is more intense, then you may have the second order optical response. But this second order optical response is forbidden in glasses because glass is amorphous and has an isotropic structure. Chi2 exists only in non-centrosymmetric crystals. So that's a pity because there is lots of properties and very useful properties that can be used with this Chi2 susceptibility. The first one can be second harmonic generation, for example, if you want to convert light frequency, but you may have also electro-optic response. And this electro-optic response, maybe you don't know, but you use it every day, each time you use internet, in fact. Each time you need to convert electrical signal into optical signal, you are using such kind of electro-optical response. This is based on such kind of approach where you have modulators with here the electric field, which can be your electrical signal, and the Chi2 multiplied by this electric field. So you see in this here you put one optical field, one electric field, and this Chi2 multiplied by the electric field will change the Chi1, will change the index in this branch. And this allows you to modulate and then to convert optical signal into electrical signal. So that's interesting, but if we look at the future and what will give in the future the photonic device and the planar device, you have here a very nice example. This is a photonic circuit which has been developed for quantum computation. Okay, so glasses can be very useful for that because this is a very complex circuit. This very complex circuits, all this part, for example, where you have lots of couplers can be done with glass, for example. But all this part here, where you have all these two electrodes, in fact, each of them, you see, it's a modulator. This cannot be done with glasses. So here, in this case, you need to combine maybe a glass and maybe then after a non-centrosymmetric crystal. That makes everything quite difficult to prepare, in fact. And so there is lots of needs for new materials in such kind of domains. And if you can see here, the number of optical functions within one optical device like this, in fact, it increases exponentially like we have seen in the past with electronics. All right, so how can we do to put nonlinear response in a glass? So we put this electric field as I told you, because my static electric field can interact with the Chi3 to give me a Chi2 and give me some response inside the glass. This has been discovered in 91. So that's an old story, very old story. In 91, they have found 0.1 picometers per volt in silica. But we wanted to compete with this very classical crystal lithium niobate, which is 60 picometers per volt. So you see there is more than 2 orders of magnitude of difference. Okay, and people have tried during years and years to try to improve this Chi2 response inside silica, but does not work. You need for this to change the glass structure, to change the glass compositions, and try to reach glasses which will obtain very high Chi3 values in order to improve a lot of Chi2 response. So this is what we have done. I will switch now quite fast during the test of Lara Karam, where we have worked on pure niobate films. So in order to improve these Chi3 values, in fact, we have removed all the glass formers. So how can we make a glass without glass formers? That's good questions. For this, you need to quench much more rapidly. And if you want to quench much more rapidly, then you may go and you need to go towards sputtering depositions that goes through a plasma. Because going to the plasma, you will increase by many order of magnitudes the quenching rate, and you can get, I will not say glassy, but at least amorphous materials for almost, let's say, lots of compounds. So this is what we have done for these niobate films. We obtained very nice amorphous materials with good optical properties. But the most interesting point is that it reacts very well to the polling. And so we can use all the methods that I have shown you before. This example here explain how we can modify the glass structure, okay, not the glass, the thin film structure locally using this imprinting method. And I want to focus more on the nonlinear response. So this is the map of the sodium repartition in the film. You see, so you have one line of 10 microns thick, and the SAG response is located on each edges of the line. And you have a very strong response. Please look at these values. It's 3 orders of magnitudes that goes from 0 to more than 3 orders of magnitudes in few microns. So it's very located. Okay, so that's it works very well. We can really imprint and locate the nonlinear response very accurately. So I've shown you the localization of the nonlinear response. That's very interesting. The second thing is the geometry. The geometry is purely uniaxial, so that's very good also. If you can look at this, I told you we have 3 orders of magnitudes, but we can completely erase this signal if we turn the sample. So it's purely uniaxial, and that's very good for applications. And now, since it's a magnitude, so we can compare the quadratic law for the single crystal lithium niobate and for our thin films, and we can see now that we reach the order of magnitudes of these very well-known crystals, and we are in the order of almost 30 picometers per volt for these thin films. I'm maybe going too fast, but I'm sorry. I'm really enthusiastic to show you all this, but anyway, if I have time, I can finish with this. Okay, thank you. Now I will show you new results that we obtained this last month during the PhD of Alice Boyot. So we were working on plasma-assisted polling for liquid crystals. So the PhD of Alice was done in collaboration, I would say, but it was a co-tutel PhD with COPL in Quebec. And in COPL in Quebec, there is Professor Galstian, who is specialist in liquid crystals. So before the PhD, we were discussing what can we do with poled glasses, electric field, and liquid crystals. So we'll try to put liquid crystals on such kind of glasses. And that was quite interesting because there is in the literature lots of different methods to do it. Okay, how can we control the liquid crystal alignment on the surface without using electrodes? Just by using, for example, patterned polymers or here some different topology. So the idea was to work on commercial glasses, and Alice has tried different kind of polling, almost all what we can do, and that was not working very well at all. But one day we said, okay, we are developing at the same time in parallel some plasma polling. So let's try with plasma. Maybe it will have a better interactions, or maybe it will be, the effects of the treatment will be more located on the surface. So I will show you one example of this kind of plasma polling. In this case, in fact, we use two strings that are just deposited on the glass. And then we heat a little bit, 200 degrees, and then we apply 1000, if I can have a video, yes, 1800 volts. If you can see, that's a very accelerated video, okay? Normally it takes 20 minutes. We can see all the plasma discharge here, going from the string in all directions. This treatment is not at all controlled, okay? It's the plasma go in all directions. But we have done the liquid crystal cell after. On the liquid crystal cells that you can see here, if you look around the string here, the liquid crystals, they follow exactly all the plasma discharge that have been uncontrollably induced during the treatment. So that's just, for me, a very nice proof that it's very effective. So let's go now on how can we control this. So Alice has tried to control this very well. So she was using not grids, not a string, but some grids. After making the plasma, you take the glass, and then you create your liquid crystal cell. If you use a grid on the proper parameters of polling, you have a very well controlled plasma emission, as you can see, that follow very well the electrical current curves. So that's much more controlled than what I have shown you before. And then we can look at the surface of the glass. We can look at the response by second harmonic generations in order to locate the fields that could be implemented inside the glass. And you can see that the fields are located at the edges of the grid, okay, and they are very polarized. So the fields, if the grid is parallel to the y-axis, the field is perpendicular, and that's very uniaxial also, like I have shown you before. Now you put the liquid crystal inside this, and you have a very nice multi-domain formation where all the liquid crystal will follow the electric field geometry that your treatment has induced on your glass surface. So, for example, here, this ECG signal proves that you have in these directions a field along the x-axis. And the crystals, the liquid crystals here, create this triangle domain, and they are oriented along this x-axis. So that's a very nice proof of concept that you can modify and add some electrical functionality on the glass surface, which will interact strongly with the molecular systems and induce its self-orientation. Okay, I hope I have convinced you that combining glass chemistry and thermoelectrical polling can be very good for multifunctional and multi-scale approach. And then I would like to thank all my collaborators, especially all the people from ISN, people which has worked on this different kind of subject. Also my colleagues from Bordeaux, of course, and the different other colleagues from France and everywhere. Thank you.
We have time for one or two questions from the audience or maybe from the internet. Please. Oh, it was clear.
I don't know.
Check. Okay. You can raise your hand by internet if you have questions also. I don't know. No question from internet.
It's okay.
Okay, maybe I have one question.
Thank you.
Concerning the last part where you explained that discharge, plasma discharge. So you have the electric field. How is following the plasma discharge?
So the plasma is created by the charge given by the glass. Okay, so the glass, you move the sodium towards the cathode, but you have the same quantity of negative charge that goes to the surface. So that increases a lot the potential on the surface. And when it's sufficiently high, then you ionize the gas between the electrode and the glass surface. And then you release the charge coming from the glass. But there is a huge reservoir of charge. So when it's released during one discharge, and after some time, it will recharge the surface and recover. That's why we have some very nice long plasma emission under DC conditions, because the glass is a reservoir of charge.
And then the liquid crystal just part something like perpendicular.
Yes, the liquid crystal will follow the surface current direction. Exactly.
Yes. Chat, maybe it's a question. Yes, you're right. So there is a question which is we have this on the board. What is the resolution of
the resolution of patterning? So for the first part of the talk, the resolution can be down to 1 micron. But for the liquid crystals, I don't know. The best we have done, because for the liquid crystals, you really need this plasma, and you cannot work with very tiny electrodes. So the best we have done is some squares of 40 microns of size. But the important is all the fact that you need enough gas. So if you work with a thin films, it's not enough. But if you have few microns of gas, it's good. So for the liquid crystals, I hope we can go below 10, but we have to try.
No more question? I don't think so. Let me check. if you have some, yes, maybe discussion. Thanks. Okay. Okay. Thanks again.
Pleasure.
Thanks, speaker again. So here we just have to switch to the next talk. So concerning the, let's say, augmented reality and how glass can play a role in reality. So this is a talk given by Antoine Picard from Corning Company. And I'm sorry about the specialty fiber for sensing. Thierry Robin, unfortunately, cannot be here, attend to the conference. So let's switch to the last part. How glass can really. Is it okay? Yes. So let me stop sharing. Yes, I think now you can switch. You have to share screen. The one.
C'est le 2.
Well, yes, I think so. Yes, I think it's okay. Perfect.
Okay, so first I'd like to thank the organizer for giving me the opportunity to present some of the work we've been doing at Corning on the high refractive index glasses for augmented reality and mixed reality application. So first I'd like to give some definitions. So you might be familiar with virtual reality, where you put a headset on and you're immersed in a fully virtual world. Here we're talking about augmented reality. So that's when you're wearing smart glasses, so you see your environment, but on top of that, you're going to display some digital information. And when we talk about mixed reality, we're really mixing the two approaches together. So now you're not just overlaying digital content, but you're really anchoring it in your environment. So there's a deeper feeling of immersion, and it's more difficult to really see the difference between the digital world and the real world. So that's really what people want to achieve at the very end. So today I'll first start by introducing Corning, for those of you who do not know our company. Then I'll try to show you how Corning is trying to serve the emerging AR/MR market. I'll explain why we need some high refractive index glasses for these two applications, AR and MR. And then I'll try to show you some challenges associated with the high index glasses in our company. So first, let's start with Corning. So Corning is an American company, was founded in 1851. So it's pretty old for an American company. Headquarters are in Corning, New York. That's also where we have the biggest R&D center. I'm coming from the second biggest R&D center from Corning, located in Fontainebleau in France. So it's about 50,000 employees worldwide. We are ranked in the Fortune 500 companies. And what we are working on, we're really a material science company, and we're trying to really use our expertise in glass science, ceramics, and optical physics to develop new materials, new application that can really have an impact on people's lives. And what is really special about Corning, I think, and I think it's important to point that out, is that every year we spend around 8% of our revenue in research and development. And that's something we do in good times and also in bad times, because we really believe that innovation is key for us to grow. And I think our track record of innovation is really showing that pretty well. So if we go way back to 1879, we have the first machine to create the glass bulb for Edison's electric light, invented in Corning. And if we go a bit further in time, we have in 1915 the Pyrex glass, which is heat resistant. A few years later, we have high purity fused silica, which is still a product that we do at Corning for optical application. We have the first silicones that were invented also by a researcher in Corning. We no longer do silicones, but that was invented in Corning. We have the first glass ceramics also invented in Corning that we use for cookware, but also for cooktops now. and for other kind of application. 1964, I think, is an important date for us because we have the fusion overflow process, which is calling proprietary forming process that is used quite a lot throughout the company. And I think it's a very interesting example of our mentality to redevelop new approaches or new material or new processes, because you see that was developed in 1964, but when we really started to use it to a large scale, it was in 1982 for liquid crystal display glass. So we were able to really develop this approach and use it 20 years after, when we had really a market that was needing it. But in between those 2 days, we didn't stop working. 1970 was the year where we made the first low loss optical fiber, and which then enabled all of the telecom boom to take place. We have also the first ceramic substrates for catalytic converters that are now in all of the fuel cars. Fast forward to 2007, we have the first tough and thin cover glass for mobile devices, and that's the now well-known Gorilla Glass that you can find on a good number of smartphone devices. 2012, we have the first ultra-thin flexible glass, which is now becoming quite useful also for phones that you can flip. And very recently, 2017, we started to work for the pharmaceutical industry, creating the damage-resistant pharmaceutical glass packaging, which enable a faster rate on the filling lines, and also more safety because the glass is more resistant to damage. And so that's something we invented in 2017, but which was really handy very recently to package the COVID vaccine. So we made a lot of those vials for this vaccine. I think I gave you a good overview of what we're doing, what kind of products we're working on. But today I'll be focusing on what we're doing to serve the AR/MR market. So I will talk mostly about glass, and so that's those high index wafers that we supply in different indices, going from 1.8, 1.9, 2.0 in various sizes. But we don't stop there. We also sell the tools to measure the geometrical attributes of the wafer through coding Propel. So we were selling the machine called the Flatmaster, which is used throughout the industry. We have also automated laser glass cutting machines that we supply through coding laser technology that enable high throughput and that can really cut those wafers to make the eyepieces at the end for our customers. So we're really trying to serve the whole market, from the glass to the machines that enable to make those devices a reality. So I'll be focusing on high refractive index glasses. So first, I'd like to show you why we need those high refractive index glasses for AR and MR. So first, you need to see what is the principle of the waveguide technology that people are using. So if this video is working, so that's a typical AR headset. So you have a micro display that will send some information to the viewer. You have typically 2 to 3 pieces of glass, of high index glasses, one for each color, red, green, and blue. And what we can do is to send the light into those pieces of glass. And as you have a high index, what's going to happen is that the light is going to travel via total internal reflection inside the glass. So the glass is going to be used as a waveguide. So you have, of course, an input conversion and an integration at the end to just send the light toward the user. And doing this, you're able to overlay this digital content onto the real world for the user to have a new experience. And what people want to do is to have an immersive experience. So they need to maximize the field of view of the image that they're going to be launching to you. And to do that, the easiest way of increasing the field of view is by increasing the refractive index of the piece of glass. That's just Snell's law, and you're working on the critical angle. And basically, as you increase the refractive index, you're going to increase the angle of light that you can send inside the waveguide. So as you can see here, the field of view is increasing linearly with the refractive index. And of course, you want to be as close as possible to the human eye field of view. If your field of view is small, it's going to limit where the image can sit in relation to the overall view of the wearer. And obviously, you don't want the image to be always in the very center of your eye, because it can be quite annoying. So you want it sometimes to be on the edge. So that's why you need a wide field of view. The bigger the field of view, basically, the more flexibility you'll have to put the image wherever you want, and the more immersive the application will be. So that's why we're trying to increase the refractive index even to higher values. So once we know that, we need to understand how we're going to achieve that. So a typical glass or pure silica, for instance, has a refractive index of 1.40, 45, 48. Really, you need to think about the light, the refractive index as a way to kind of measure the speed of light in your material, because it's the ratio of the speed of light in a vacuum to the speed of light of your medium. So what you need to do is to really increase this refractive index, basically by two means: by increasing the polarizability of the glass, or by reducing the molar volume of your glass. And how do you do that? It's by stuffing your glass with more electrons, basically. So we're not going to be talking about typical glass like silica and a few modifiers. What we're going to do here is to add a lot of transition elements. So we can add titania, zirconia, niobium, tantalum, tungsten, something with lead or thallium would be extremely useful to increase the refractive index, but obviously we can't use them for obvious reason of toxicity. But we can also use some elements in the lanthanide series. And basically, we're trying to add the more polarizable ions. So it seems pretty straightforward, but obviously, all of that is going to come with some trade-offs. So the first one is obviously density. So as I told you, we can have up to 3 pieces of glass for each eye. So if the density is increasing too much, your headset is going to be very cumbersome, and it's not going to be a good experience for the user, because it's not going to be able to use it for an extended amount of time. So the game is then for us to find the right combination of elements that can increase the refractive index without impacting the density too much. We have another requirement, which is transmittance, because as I told you, we're setting light in red, green, and blue. Red and green, we don't have any issue. The glass, all of our glasses are fairly transparent in those wavelength region. The blue is really the difficulty for us, because as we increase the refractive index, we're going to tend to shift the UVS toward the visible. So we're going to be lowering the transmittance in the blue. And we can't afford to do that, because the optical path is actually quite long. It's around a few centimeters long. So if we're sending red, green, and blue, and the blue is partially absorbed, for color uniformity, it's not going to be good, because we're going to absorb some part of the blue light, and the color are going to be distorted, basically. And if they want to compensate for that, we can think about increasing the power on the blue light, but then you're going to reduce on battery life. So that's why we need to maximize the transmittance in those 3 regions. Manufacturability, that's for us in the plant. So we need the glass to be still manufacturable. And as we increase refractive index, typically the glass are becoming less and less stable, and which is quite difficult for us when we need to produce them in high volume. And they tend to devitrify, basically. And also they are very fluid, which is more difficult for us to put them, to cast them properly. Obviously, there are all kinds of other properties we have to look at, also chemical durability. because those pieces of glass are going to be used as wafers, so they're going to be going through different cleaning steps in the industry that will create those AR headset. We have some mechanical properties to meet as well. So it's a whole set of properties that we need to keep in mind. And obviously, a lot of them are kind of contradictory. So for instance, usually when we try to boost transmittance by using specific elements, we decrease the manufacturability because the glass are going to be less and less stable. Same thing if we want to decrease density, usually we decrease transmittance as well. So it's very difficult for us to find the right balance, and that's basically the work we've been doing. Just to show you some example of some of the situation we're facing. So if we look at the refractive index versus density, you see that usually as we increase density, the refractive index is increasing. We have some points which seems to be not following this trend. Okay, we have some points on the upper left corner that are not following this trend. That's when we're using different elements, combination of elements in the glass to try to minimize density. But usually those points, as I told you, are going to be glasses which have lower transmittance, so it's not going to be interesting for us. So the work then is really to find the right balance to have the best of all of the attributes. Same thing for internal transmittance versus density. You're going to see that if we are okay with low internal transmittance, we can reach rather low density. If we want to maximize the internal transmittance, usually it comes with the price of the density. We have to compromise a bit on this parameter. So that's really the work we've been doing. So that's for finding the right composition of glass. But now we need to take it to the plant. We need to melt it. So you need to find the right process to make the glass and to reach the properties that you want. And what I wanted to show you here are some pieces of glasses that we made in the lab. So they're always the same composition, and we are just changing. We're just changing the way we process it. So in the way we melt it by changing some temperatures, time, some raw materials, and you can see that for same composition we can go from 77% of internal transmittance. When I say this number, it's always at 460 nanometer in the blue. And we can go up to 97% of internal transmittance. So you see that the key, once you have the right composition, is to process it the right way to really achieve the best of the results you want to reach. And when we are able to combine all of that, I want to show you what we can achieve. So here on this plot, you see some data points from the lab, and in red you have the Corning 1.88 glass that was made before, which was a glass for ophthalmic application. So it was really for just lenses. And for this application, you don't care about the internal transmittance to be so high because the optical path is really thin. It's just going through the eyepiece. So this glass was made for lower density and high refractive index. So we were at 1.88 of refractive index, around 92-93% of internal transmittance at 460. And the glass we developed for AR is this one here. So first we increased the refractive index to 1.90, and then we were able to achieve in the lab internal transmittance above 97%. This glass is now in production. That's Corning new 1.9 glass for augmented reality. And obviously, we keep on continuing to work on higher indices. So in January this year, we announced the Corning 2.0 high transmittance glass for augmented reality. And this work is a continuing story. So I showed you how we make the glass composition, how we melt it, but now we need to form it. And we have some challenges there also in manufacturing. So here I'm just showing the viscosity of some glasses. So the first one on top, the green plot, is the typical viscosity curve of a flat panel of glass used for flat panel display, so display glass. And in black, you see a typical high index glass. And the first thing you can see is that the viscosity is much lower for those high index glasses. So we are in a very different regime. We are of only few points at around the liquidus temperature. So you can imagine that to form this glass is going to be very different. For a display glass, we use the Corning fusion draw process, where basically we feed the glass from above, the glass overflow, and then from the two sides of this trench, the glass are going to be fused basically, and you're going to make that pristine sheet of glass, and which is very good to have some geometrical attributes, and it's very good because your glass is not touching any surface. So you make a very clean sheet, and that is how we were able to really increase the size of the flat panel that we can supply. So you see that in the 90s, we were at Gen 1, Gen 2. The dimensions were pretty small, and now we are at Gen 10.5. You are at 2940 millimeter by 3370 millimeters. So it's becoming to be very big, and that's key to enable mass production, basically, to cut down on cost. And so you see that once you have the glass composition, you really need to have the right process to make it to go to mass market. This we cannot use with high refractive index, just because the viscosity is just too low. It's not going to work on this kind of asset. So you won't be able to form a sheet of glass. It's just going to drop from this asset. So the process of record to make those high index glasses is very different. So what we're doing is casting glass blocks. We cold drill them, we wire sew them, and then we lap and polish into wafers. So you can imagine that this whole process is very long. It's also quite costly. So as I told you, we are really a research and development company. So there's still a lot of work going on to either increase the refractive index or work towards new ways of shaping the glass to make it a more efficient process. So there's still a lot of work to be done here. And I'd like to point out also that it's just not the work of one person. It's really a teamwork from all across the Corning world. And we have people involved in glass research, development, engineering, and characterization. And it's really the work of all of these persons that enable a success like this. And to finish, I just wanted to show you the vision of the augmented reality that we could have. That's what a video that we launched when we announced the Corning 2.0. So I don't know if we have sound here. I'm not sure you're hearing, but basically it's showing what the future could be with a Corning glass on all of the AR headset. I'm not sure you have the sound, so you can watch it on YouTube later on if you want, and you'll see what the vision we have for those products. And we think we can stop there because I'm not sure you're hearing. And if you have any question, feel free.
So for sure, we have time for questions. Already one. We can start from the audience. Some question? Yeah. Question from Marcelo. Marcelo Nara. Yes, Marcelo, you can talk.
Okay, thank you, Lionel. I would ask you if you can say something about the glass composition, in fact, for this kind of glass. Are you using or have you studied something about the niobium-based this glass to increase the refraction index and use it for this kind of lens?
So of course, niobium is one of the elements we can use, but we don't rely on only just one element. It's really a mix of all of those elements that can increase the refractive index. So obviously, I can't go into too much details, but you can imagine using a mix of those elements. So niobium is part of it, but we also have access to lanthanum, yttria, zirconia, tungsten. Basically, we'll be trying to use the elements that can increase the refractive index without having too much impact on color. So if you look at the optical band gap of some of the pure oxide, you have a good idea of some of the elements we could be using to make those glass possible.
Okay. So. No question? We have another question?
Does changing the index change the TG of the glass?
Yes. Okay.
So yes, it does. But we are usually working within the same glass family, so the TG are not changing too much as we increase the refractive index. But the biggest change we have is if we change glass family. So if we go from borate, silicoborate, phosphate, and things like this, that's where we would have the biggest change of refractive TG, and not be with refractive index, but more with the glass family.
Yeah. One question from Thierry. Thierry, louder because I don't think they can hear you. Before.
Oh, you mentioned in fact leaky.
Yes, leaky grading. So it's just so I'm not an optical physicist, so my explanation is going to be pretty terrible probably, but it's just that it's a grading that is pretty long, and they use a leaky grading, I think, to really expand the image that they're going to be launching. So I won't be able to give you all of the details just because I don't know all of the details, but that's really, I think, an optical trick to really improve the quality of the image they're launching. Yes. It's on the surface of the glass. So the incoupling grading and the leaky grading are deposited onto the glass surface.
Mark, any question? Okay. Okay, do we have some other question from the Zoom meeting? No, not from the chat. Okay. So, if no, let's thanks all the speaker and the speaker. So this is it was the last series of conference concerning the glass. So you know that we are in the year of glass. So this is very nice to have these 5 meetings in 5 universities with many companies from everywhere. You see that with these different meetings, someone raised the hand. Marcelo Nara, still want to ask a question? Marcelo? No, maybe not. I think you just forget to, okay. Okay. So I think that we have many applications from glass and new glass, and how glass can really perform in companies, and with many new applications. So this was very nice during those 5 weeks. And you can follow us also on YouTube. So if you don't see the conference, you can see on YouTube and have the conference on YouTube. And okay, so thanks to all of you, and thanks to the speakers.